The main takeaway is that SPADE allows language models to continuously self-improve by designing their own training environments. Traditionally, AI agents are trained on static datasets or fixed simulators, which they quickly exhaust. SPADE changes this paradigm by using a single large language model to play two distinct roles. First, it acts as an environment designer, writing complete, interactive training tasks as executable code. Second, it acts as a reasoning agent, learning to solve those very same tasks. This dual-role self-play creates a continuous, open-ended loop of coevolution and self-improvement. The core problem is that static training environments limit how far language agents can scale. Currently, building interactive environments with verifiable rewards is a massive bottleneck, costing industry labs millions of dollars. Whether these environments are hand-built or synthetically generated, they remain a fixed pool. As the learning agent improves, it eventually masters all available tasks, and its progress plateaus. To achieve true open-ended intelligence, we need training environments that dynamically adapt and grow in complexity alongside the agent. The first major breakthrough of SPADE is representing entire interactive environments as executable Python code. Instead of generating simple text questions, the environment designer writes a complete Markov decision process using a standard gym-style interface. This means every generated environment contains its own state transitions, reward functions, and verification code. By using code as the environment representation, SPADE can unify single-turn reasoning tasks and complex, multi-turn tool-use scenarios under a single, highly flexible programmatic interface. The key methodology for training the designer is a novel hint-based regret reward. If the designer was a pure adversary, it would simply create impossible tasks to defeat the agent. To prevent this, SPADE requires the designer to generate a privileged hint alongside the environment. The designer's reward is then calculated as the gap between the agent's performance with the hint versus without it. This clever mechanism ensures that environments are mathematically solvable with the right insight, while remaining challenging enough to push the agent's learning frontier. To prevent the self-play loop from collapsing, SPADE incorporates corpus grounding and environment memory. Without external input, self-play models suffer from mode collapse, repeatedly generating the same simple tasks. SPADE solves this by grounding the environment designer on freshly sampled documents from a massive pre-training corpus, seeding new and diverse topics. Additionally, an accumulated environment memory tracks past tasks and their regret scores, ensuring the designer avoids repeating mastered concepts and focuses on what the agent currently finds difficult. The experimental results show that SPADE significantly outperforms fixed environment baselines. When evaluated on held-out math, science, and coding benchmarks, SPADE achieved an average improvement of over 5 points compared to the strongest static baselines. In multi-turn tool-use settings, the gains were even more pronounced, with a massive 13.9-point lift on AC Bench Agent. Crucially, the performance gap between SPADE and traditional methods grows wider as the model scale increases, proving the effectiveness of adaptive training. An exciting emergent behavior is how the agent shifts its strategy from front-loaded guessing to active hypothesis testing. Early in training, the agent attempts to derive the entire solution in advance, failing if the environment rejects its formatting. Late in training, the agent learns to interact dynamically. It probes the environment first, gathers evidence, tests short hypotheses, and only performs long-form derivations once it has collected sufficient information. This mirrors how humans solve complex, interactive problems. In conclusion, SPADE represents a major step toward open-ended self-improvement in AI. By turning environment design into a learnable, RL-trained component, the system allows models to co-evolve their reasoning skills alongside the complexity of the worlds they build. While limitations remain, such as complexity being bounded by the base model scale, future directions point toward fully automating the post-training pipeline. SPADE shows that the key to building smarter agents is letting them build their own classrooms.